Hi everyone, welcome to my presentation. My name is Yiheng, and today I'm going to tell you a story about using artificial intelligence to optimize the measurements of radiation isocenter in radiotherapy Linacs. I'm very lucky to have Pejman, Mubashar, and Hans as my supervisors. So first, Linac is an isocentric treatment machine. As we can see on this picture, the axis of rotation of the gantry, the blue one, the collimator, the red one, and the couch, the green one, all intersect at a point, and that's the mechanical isocenter. So we have few advantages of isocentric treatment. First, it involves less patient positioning as the gantry, the collimator, and the couch are all rotating around the isocenter. Then, isocentric treatment offer an option for arc therapy, for example, VMAT, so that we can spread the dose to normal tissues to a larger volume. And sometimes this is beneficial to patients. So besides mechanical instability, there are some factors influencing V to have an isocentric radiation field. We may have displacements of the focal spot or the flattening filter. So this just gives us a perfect visualization of how these two displacements will affect this. So if the focal spot is perfectly aligned with the top of the FF, and the beam profile will be flat, will be symmetry. However, if it's not, the beam profile will be oblique, and we will have a non-isocentric radiation fields. Also, if we are using MLC, and there are MLC misalignment, the radiation fields might also be non-isocentric. So we need radiation isocenter to measure this. Basically, radiation isocenter means the intersection of central axis of beams from different directions. Ideally, it's a point. In practice, it becomes a volume, and the size of this volume matters. According to AAPM test group 142, the size of radiation isocenter should be below 0.5 mm for stereotactic treatment and below 1 mm for non-stereotactic treatment, and this should be checked annually. So we need a method to check the size of radiation isocenter. Starshot analysis is a commonly used method. It is usually film-based, so we place the film perpendicular to the axis of rotation of the gantry or the collimator or the couch. So these are two different setups for the measurements. And after irradiating the film, this is what we will get. Starshot pattern on a piece of film. So after we got this, we need to do 3 steps. First, we need to deal with the noise. Then we need to find the beam central axis for each beam. And finally, find the smallest circle intersecting with all beam central axes. This smallest circle is radiation isocenter we want. And its radius is the size of radiation isocenter. So here we can see, first we need to find beam central axis for each beam, and then we find the smallest circle. So here are 2 main literatures talking about starshot analysis. The first is the work done by Dupuy et al. So in their work, they use an analytical solution to find the smallest circle instead of using some commonly used gradient-based algorithm. So the analytical solution basically says, on a plane, the smallest circle intersecting with all lines occurs as the largest inscribing circle of all the triangles made by all these lines on this plane. So I'll talk about that later too. And the second one, the work done by Stoksky et al., is which I find most relevant to my project. So first, instead of only use films, they also used EPIT to measure the radiation field. And the advantage of using EPIT is that by using EPIT, we can have only one beam on one single EPIT image. And what this can offer is, after image processing, we can digitally superimpose all the beam central axis on one single image. And we can compare this digitally superimposed image to the image we acquired on the film, where we just irradiated the film from different directions. So by comparing these 2 different types of images, Stoksky et al. Find that if we are using beams from opposing angles to irradiate the films on the film like the traditional way, and we are likely to underestimate the size of radiation isocenter, which means we will overestimate the accuracy of the Linac we use. And they have another finding which kick off my project, is that when they're measuring the size of radiation isocenter of collimator rotation, and when they are choosing different gantry angles, the size varies as the gantry angle changes. So here we can see that's the smallest circle occurs as the largest inscribing circle. And here we can see the size of radiation epicenter will change as the gantry angle changes. The blue and the red are just for variant geology and for true beam. So all the previous work, they have done amazing work about analyzing starshot patterns. Their accuracy is incredibly high. There are problems, for example, when we are having multiple beams on one single image, which is called composite image. And those beams will affecting each other in image processing. Well, that can easily be fixed by using EPID, right? But there's another problem. When we are doing starshot analysis, we are using finite number of beams. And those beams coming from angles that are usually randomly chosen with few scientific evidence. So the real problem is that we are trying to use starshot to represent radiation epicenter. But are we looking at the true radiation epicenter, right? So if we chose the angles that give smaller sides of radiation epicenter, and we think that is what we are going to measure, and use that to check if it's within that tolerance. And then we are using other angles which give larger size of radiation epicenter for treatments. We are overestimating the accuracy of the Linac. So for treatments like SRS, which require very high accuracy, this is not what we want. So what my project is I'm going to tackle this problem. I'm going to try to find the radiation epicenter as close as we can achieve to the true one. So my aim is to optimize the measurements of radiation epicenter of collimator rotation in radiotherapy Linacs. I will give recommendations on gantry and collimator angles to choose for starshot tests. So first, I'll introduce a concept, optimal collimator angles, OCAs. So it means radiation epicenter defined by OCAs at a certain gantry angle for a beam energy on a certain Linac. It's the closest one to the true radiation isocenter. Or you can understand it by, say, the OCA maximize the radius of the inscribing circle of the triangle. I'm going to figure out two relationships. First, I will figure out the relationship between the radius of the inscribing circle and the triangles of the collimator angles. Then, the relationship between the OCAs and the gantry angle, the beam energy, the machine, and probably the machine type. So what I'm going to use for my project, first I will use MATLAB. Then DICOM images. Those images are acquired on 8 Electa Linacs based in Denmark. On each Linac, we pick 2 beam energies, 6 and 18 NV. At each beam energy, we have 13 gantry angles, 0 degrees to 360 degrees. And at each gantry angle, we also have 13 collimator angles, again 0 to 360 degrees. So the measurement is done 6 times. In 3 times, the gantry rotation is clockwise. In the other 3 times, the gantry rotation is counterclockwise. So totally, there will be more than 16,000 of DICOM image. This is one of those images. This is what it looks like in MATLAB. Potentially, I might use some more data, which includes similar but less data acquired on variant Linacs, and I might also do some film measurements, and the films will be scanned and to be dealt as my data. So 2 steps involved in my project. The first one is image processing. First, in image processing, I'm going to deal with the noise, or it's better to say the signal-to-noise ratios, SNRS. So we want to increase this ratio as high as possible. So here is just a figure showing the relationship between the SNR and the deviation of the size of radiation epicenter. So we can see when we are having a low SNR ratio, the deviation is huge, and we don't want that. However, if you increase the SNR to above 10, and if we further increase them, the deviation is fairly small, and that's my goal. That's what we want. So in order to increase S and R, we need to filter the pixel value curves that we'll acquire from the images. So there are three main filters to choose: Gaussian, Sawatsky-Golay, and Wiener. I will compare the performance of these three filters on my data and see which one works best. Like, for example, has the highest repeatability. This is a figure showing, so the left one is the pixel value curves before filtered, so we can see there's a lot of noise. The right one is the one after filtering, so we can see it's much more smooth, and we can easily find the zero crossing, which stands for the beam edges. After dealing with the noise, I'm going to find the beam central axis. So this is fairly simple. First, find point pairs on beam edges, then find midpoints for each pairs. So we can see here, the left one is an image. So there's two green lines on the beam edges, and we took that as the pairs. And then the blue one in center, we took that as the midpoints. By using all the midpoints on one beam, we can fit a linear equation. And this linear equation will represent this beam on the image. So different ways to do that, and we'll choose a different number of pairs. So Gonzalez et al., they chose 6, as we can see here, 6 pairs on one beam. Deployed, they choose 10 pairs. Well, what I'm going to do, I want to choose as much as I can. So as we can see in that picture, we have chosen a lot, probably all the points along beam edges. I'll try and see which one works best. So after image processing, I'm going to do optimization. First, find the smallest circle. I'm not going to use the gradient-based optimization. I'm going to use analytic solutions. Again, smallest circle intersecting with all lines on the plane occurs as the largest of all the inscribing circle of the triangles, which can be made from all the lines on that plane. So at each gantry angle for each beam energy on each Linac, I will find all possible combinations among the arbitrary selections of 3 collimator angles in a group. So because for each condition, we'll have 13 collimator angles, which give us 286 different combinations. So a list will be generated, and the list will contain the different combinations of collimator angles and the radius of inscribing circle. And you put them in a descending order. So R1 is the largest radius, and the 3 collimator angles that give R1 is our OCA. So next, after finding the OCA and their radius, I'm going to find the OCA's dependence on the gantry angle. So we use the same beam energy on same Linac, and we change the gantry angle and see how OCA changes. And OCA's dependence on beam energy, same gantry angle, same Linac, how the OCA changes between beam energies. Also, OCA's dependence on machine, same gantry angle, same beam energy, how OCA is going to change between machines. So with this dependence, I can find the relationship between the OCA and the gantry angle, the beam energy, and the Linac, and that will give us recommendations on gantry and collimator angles to choose to perform star-shot test. I'm going to skip this now. So my study plan, this semester I'm doing research development. It's basic done. In the summer, I'll start do the image processing, involves dealing with the signal and noise and find the beam central axis. So I will work full-time on my project during the summer. So this will be done before the beginning of next semester. In next semester, I will do the optimization, which is find the radius against and their relationship against CA, collimator angles, and the OCA against gantry angles, and beam energies and machines. So hopefully by the end of next semester, I've done all the research part. So during the winter vacation and my last semester, I'm going to write the papers for publication. I run my thesis. So studies is no similar project has been undertaken here at Charlie's. In monthly QA, we use variant isoco phantom to check radiation isocenter, which look like this. And annually QA and commissioning, we use stars analysis, which is analyzed manually like this or using commercial software PIPS Pro. So problem is that this is a data-intensive project, involves more than 15,000 of DICOM images, so the computing power might be a problem. The cost involves MATLAB student package and for 2 bucks, which costs $180. Potentially, I might need to purchase more 2 bucks, which costs $35 each, and I might need to use some films, which cost approximately $800 per box. Fortunately, all costs are covered by our medical physics research group and the Department of Radiation Oncology. So here's some of my reference. That's it. Thank you for your attention.
You are using the EPID for imaging, isn't it? That's the plan?
That's already been done. So the image are the measurements already been done 5 years ago in Denmark by one of my supervisor, Hans. So he's going to give me all the images and I'm going to analyze them.
Yeah, that's right. But what do you think, because you're using an EPID arm itself is actually not this stable.
Yeah, exactly.
So how you get this sort?
Yeah, so the APID is attached on the gantry and there's gantry sac. So fortunately, if we are using the same gantry angle, so what I'm doing is that at a certain gantry angle and I rotate the collimator. So all the relationships I'm going to find in this gantry angle has nothing to do with the gantry sac. And I'm also using the whole 360 degrees gantry angle. And so I'm not trying to build relationship with both changing 2 parameters of gantry angle and collimator angles. So I'm going to keep the gantry angle fixed, and I'm going to change the collimator angles and see what's going on. And yeah, but if I want to find the relationship with different gantry and collimator angles, I need to fix the gantry sac. So 2 of our previous students, Luke and Brandon, their works are partly on this. So I will read their thesis and I will borrow some conclusions from them and to use that to fix it.
So all of these data you're saying are done on Elekta. Are we going to use our ProBeam, for example?
Yeah, so
I missed the beginning part of the talk. But
Sure. Oh, okay. So you mean all the data, right? So
you said you have the data from 8 Linacs in the
yeah, those measurements are already been done on Elekta Linacs, and that's all the data I'm going to have. Pachman has also some extra data acquired on Varian Linacs. I'm not sure if it's done here, so I might use those to compare the performance between 2 brands. And I might use our Linacs downstairs to do some film measurements. So on what? I will use film and put that perpendicular to the axis of rotation of the gantry, and I will perform that.
Okay.
Yeah.
Why do you think you need to go for all the possible angles that you possibly can instead of just doing some select measurements?
Sorry, what do?
Go back a couple of slides.
Yeah.
You said you were going to get as many possible
Oh, there.
combinations as possible. Why did you want to do that?
Why do I want to do that?
Yeah.
Okay, so what I'm going to do is it's not what I'm going to do. So Stocksky, what they done is they put they digitally superimpose the beam central axis of different collimator angles on one image, yep, and find the largest inscribing circle.
Yep.
So why I do this? What I'm going to do is I will put 3 beam central axis on one image, and I find the radius of inscribing circle. Okay, and so how many ways can we combine the 13 beam central axis on a plane? There are 2, 8, 6 different combinations. So in all those combinations, we find the radius of the inscribing circle for each combination. The largest one is definitely B, the one. Then I put the 13 beam central axis on one image, and the largest one I get is the same one.
About how long does it take you to do that?
You mean take me to write the codes or take the computer to?
Both. For your 16,000 images.
Okay. For me, it's not a big deal because like I think it's the same code, need minimal modification for all the different gantry angle or beam energies. Yeah, for the MATLAB, it's not for the MATLAB. For the computer, I'm not sure. So like if I'm using my computer, maybe it takes centuries. But like Pejman told me, fortunately we have a brilliant computer just here, so I might be able to use that, and that will take just like. But I'm not sure about that. Okay. That might be one of the problems like this.
Maybe,
yeah.
Any other questions?
Okay. Thank you.